Hello everyone. So today we are going to talk about probability, especially discrete probability. So to talk about probability, let's first check two definitions: sample space and event. So the sample space is the set of all possible outcomes, and an event is a subset of the sample space, whose probability we try to calculate. So let's try the first example. 1. Suppose a die is thrown. What is the sample space? What is the event where the number on the face of the die is an even number? So sample space is also always denoted by the set S, and in this case it's 1, 2, 3, 4, 5, 6. This is our sample space. And the event space, that set is denoted by E, and this set is the even numbers on a die, so 2, 4 and 6. So what's the size of the sample space? 6. What's the size of the event space? 3. So the probability is the size of the event space over the size of the sample space, 3 over 6, which is half. So the probability that if you throw a die, that even number will show up is half. Let's try the definition. Suppose the sample space S has a finite number of outcomes, which is important here, finite, and each outcome is equally likely, so that's also important. Like for this example, in the die, each face they show up, that probability is equal, that 1 will turn up, the 2 will turn up, 3 will turn up, they are all equal. So that is a fair die. That is also important. Then the probability of the event E is P of E equal to the size of E over the size of S. Let's try another example. Example 2. Now 2 dice are thrown. What is the sample space? So if 2 dice are thrown, what is the sample space? What are the outcomes? We know that it can be 1 1, 1 2, 1 3, 1 6, 2 1, 2 2, 2 6, 3 1, 3 2, up to 6 1, 6 2 to 6 6. So that's our sample space. The size of the sample space is 36 or 6 squared. Now let's see what's the event space for this particular problem. The event space is the sum of the number of the faces is equal to 7. That means 1 6, 2 5, 3 4, 4 3, 5 2, 6 1. Size of the event space is 6. So the probability is the size of the event space over the size of the sample space is 6 over 36, which is 1 over 6. Example 3 is, A computer program generates random bit strings where generating a 0 and 1 is equally likely. So when it generates one bit, 0 or 1 comes up with probability half. Now it generates a string of length 8. What is the probability that it generates the following string? A. A is all 8 zeros. So 0, 0, 0, 0, 0, 0, 0, 0. Okay, 8 zeros. The first one, the probability of it being 0 is half, 0.5. The second one is 0.5. Third one is 0.5. All of these are 0.5. So the total probability is 0.5 times 0.5 times this. So the answer is 0.5 to the power 8. Now the first 0, the probability is 0.5. This one is 0.5. This one is also 0.5. All of these bits, them being 0 or 1, is 0.5. So the answer is again a product of all of this. So the probability is 0.5 to the power 8. Now let's do C. A string with 2 ones and 6 zeros. So how many strings are there with 2 ones and 6 zeros? Now that is a problem from the counting chapter. So there are 8 positions, 2 of them are ones. So how many different ways can you choose 2 positions from 8 positions? This many ways. So this is your event space's size, and sample space is how many total strings are there. Total number of strings, that is 2 to the power 8. So the probability is 8 choose 2 over 2 to the power 8. Next, let's do example 4. Suppose 5 cards are chosen randomly, uniformly from a deck of 52 cards. What is the probability that we get a full house? So if you remember, full house was 3 of a kind and a pair. For example, let's say it's 7 of hearts, 7 of spades, 7 of clubs, 9 of clubs, and 9 of diamond. So these 3 of a kind, and this is a pair. So how many different ways that can happen? This is a counting problem, and we have done that in the counting chapter. How many full of a house are there? So first choose the kind for the 3 of a kind. So that is 13, choose 1. Then choose the 3 suits for this. So 4, choose 3. Then there are 12 kinds left. You cannot use this one, so from those 12 you choose one for the pair, and for that you choose 2 suits from the 4 suits. So that is your numerator or your event space size. And what's the size of the sample space? You are choosing 5 cards from 52 cards. So that's your probability. If we solve this, this is 13 times 12 times 4 times 6 over 52, choose 5, which is 6 over 41, 65, close to 0.0014. B. All 5 cards having the same suit. So that example would be, let's choose one suit which is, let's say, hearts. So 2 of hearts, 5 of hearts, 7 of hearts, 9 of hearts, and J of hearts. So that's one example. So how many different, what is the probability here? How many different ways can we choose 5 cards like this? So first choose the suit. From 4 suits we choose one suit. Then from in that suit there are 13 cards, and you choose any 5 of them. The denominator is the sample space size. That's still same. 52, choose 5. If you simplify this, you get 4 times 13 times 12 times 11 times 10 times 9 over 5 times 4 times 3 times 2 times 1. And here 52, choose 5. So this is close to 0.00198. Next, let's go to probability theory that gives us a more general approach. So even if we do not have all equally likely, all these assumptions, we can still calculate some probability. So the definition is, if S is a sample space with finite number of outcomes, we assign a probability P of S for each S in that set, such that probability of any event is between 0 and 1, which is very important. And if you add the probability of every element in the sample space, that adds up to 1. The probability of the whole sample space is 1. So let's go to definition. If you have an event E, then the question is, if S is the sample space, so what is the probability of sample space? We just learned that is 1. And what is the probability of an empty event? If nothing is happening, then the probability is 0. Next question is, when the outcomes of S are equally likely, what is P of S for each S? Then P of S for each S is 1 over the size of S. That's the equally likely case. So after learning this more general approach, let's do the next example 5, that is 3 men are seeking public office, A, B and C. Candidates A and B have the same chance of winning, but C is given 3 times the chance of winning compared to A and B. Please assess the probability of each person's winning. That A and B, they have the same chance of winning, so P of A equal to P of B, and C has 3 times the chance of winning compared to A. So P of C is 3 times P of A. And we also know that P of A plus P of B plus P of C, they add up to the whole sample space. So the probabilities add up to 1. So now replace these values, P of A plus P of B equal to P of A. So we can write P of A here. P of C is 3 times P of A. So 3 times P of A equal to 1. So we have 5 P of A is 1. That means P of A equal to 1 over 5. So P of B is also equal to 1 over 5, since it's the same as P of A. And P of C is 3 times P of A, so 3 over 5. That's how we can calculate the probability of each of these persons winning. Next is theorem 1. If P is a probability distribution over S, E and E prime are events, the following are true. Probability of E is equal to 1 minus probability of E complement. That we can prove using the complement theorem from set theory. And the second one is probability of E union E prime is equal to probability of E plus probability of E prime minus probability of E intersection E prime. That can also be proven using the exclusion-inclusion principle from set theory. Now let's do example 6. What is the probability that at least 2 people among a group of n people have the same birthday? Assume that it is equally likely for a person to be born on any day of the year. And also we are going to assume that it's a regular non-leap year with just 365 days. So the probability of at least 2 people with same birthday. Okay, so that's what we are trying to calculate. Now, using the complement method for probability, what is the complement of this set? At least 2 people with same birthday. No 2 people with same birthday. So if we can calculate the probability of the event that no 2 people with same birthday, and we can subtract from 1, then we'll have the answer for the original problem. So what does that mean, that no 2 people have the same birthday? That means each of the n people have different birthday. So there are n people in the room and all of them have different birthday. So how many different ways that can happen? We know from the counting examples. P 365, n. Now this P is for permutation, not probability, remember that. And what's the denominator? 365 to the power n. That is your answer. Now let's do the last problem, example 7. What is the probability that a positive integer selected at random from the set of positive integers not exceeding 100 is divisible by 2 or 5? So let's define some sets. Let's say E is the set of positive integers not exceeding 100 and divisible by 2. E prime is the set of positive integer not exceeding 100 and divisible by 5. So what is the intersection? Set of positive integer not exceeding 100 and divisible by 2 and 5. Now let's calculate each of their sizes. We can use the formula. Our solution for this problem is divisible by 2 or 5. So probability of E union E prime. And we just learned the formula. This is probability of E plus probability of E prime minus probability of E intersection E prime. So what is the probability of E? Set of positive integers not exceeding 100 divisible by 2. So how many are there? How many integers are there? There are total 50. And the denominator is 100. What is for E prime? There are total 20 positive integers not exceeding 100 divisible by 5. So this minus how many positive integers not exceeding 100 are there, which is divisible by both 2 and 5. There are only 10 over 100. So that is 63 over 100, which is 0.6, the final answer.